In the beginning, there existed a vast and dense mass of matter. This mass underwent an influence that led to the formation of particles, stars, and structures we observe today. For a long time, this has been the explanation proposed by physicists. However, recent research presents a new perspective suggesting that the universe may not have originated as early as once thought. It could instead be part of a cyclical process in which the universe experiences repeated phases of expansion and contraction. Brian Cox, a prominent physicist, questions the traditional notion of an ancient singular Big Bang, arguing that something cannot emerge from nothing. This line of inquiry adds an intriguing dimension to the discussion. Additionally, findings from the James Webb Telescope challenge the idea that the Big Bang was the definitive start of the universe. This raises the fundamental question: if the Big Bang was not the beginning, then what was? Join us on this exploration into the early stages of the universe as we delve into the fringes of the Big Bang and seek answers to this inquiry. If you want to stay updated with the latest news about the universe and its natural phenomena, subscribe to our channel, give us a thumbs up, share this video to reach more people, and activate the notification bell. Researchers have developed a comprehensive understanding of the universe's earliest stages, known as the Big Bang theory. According to this model, the universe was once much denser and hotter than it is today. Approximately 13.8 billion years ago, all the elements that comprise our reality were formed in a fraction of a second. During this period, the universe was as small as a peach and had an unimaginable temperature exceeding 1,000,000,000 degrees. Interestingly, this remarkable narrative continuously evolves as new discoveries are made. Astronomers have examined everything from the remnants of electromagnetic radiation from the early universe to the abundance of lightest elements, consistently finding that their observations align with the predictions of the Big Bang theory. To the best of our knowledge, this model accurately reflects the reality of our universe. Nonetheless, despite its strong empirical basis, we recognize that the Big Bang theory does not provide a complete picture. There remains an enigmatic piece of this puzzle: the fundamental descriptions of the universe. This challenge is largely due to the limitations of our existing theories. The combination of general relativity and high-energy particle physics gives us a robust theoretical framework, yet as we probe deeper into the universe's fundamental properties, the mathematical complexity increases significantly, revealing areas where our current systems cannot provide satisfactory solutions. One sign of this difficulty is the presence of a singularity, a point of infinite density at the beginning of the Big Bang. This concept suggests that the universe was once compressed into an infinitely small and dense state, which poses a profound challenge. To address this, we need to explore new frontiers in physics and develop a framework that can withstand these limitations, offering a more complete understanding of the universe's fundamental origins. Our current instruments and theoretical frameworks are insufficient to tackle this challenge, necessitating the development of new physics that can integrate and explore gravity alongside other fundamental forces at extremely high energies. This is precisely where string theory comes into play. String theory aspires to be a comprehensive model that unifies gravity with other fundamental forces, especially at super high energies. It proposes explanations for the fundamental characteristics of the universe, introducing the concept of an aeon, derived from the Greek word meaning age or era. This idea suggests that the Big Bang we know was the result of a prior event, indicating it may not have been the absolute beginning but rather part of a continuous cycle. The possibility of a cyclic universe has sparked the development of a related theory known as cyclic cosmology. While the concept of a cyclic universe has been contemplated for a long time, string theory provides a robust foundation for this idea. According to cyclic cosmology, the universe functions as if it perpetually cycles between expansions and contractions, extending infinitely into the past and future. This cyclic cosmology theory was proposed by the renowned physicist Roger Penrose, a Nobel Prize laureate. Penrose was captivated by a remarkable mathematical relationship between the early universe characterized by extreme density and the future state of the universe, which is predicted to be cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically indistinguishable under extreme conditions. Despite seeming perplexing, the total absence of matter could be the driving force behind the emergence of all matter we observe today. From this perspective, The Big Bang arises from what remains mysteriously after all matter in the universe has been consumed by black holes, eventually dissipating into dispersed photons within a vast void. The universe emerges from a state that, from another viewpoint, closely resembles nothingness, though this nothingness still represents a form of existence, a real universe but an empty one. The key lies in understanding how a similar state can be interpreted as both a cold void universe and a dense universe, depending on the perspective. The crucial insight into this understanding comes from a complex mathematical approach called conformal transformation, which is a mathematical change that alters the size of an object while preserving its shape. Roger Penrose demonstrated that the cold void state and the hot dense state can be connected through this scale transformation, altering their spatiotemporal properties despite their differences in size. However, Penrose argues that time loses its significance under these extreme conditions. In cyclic cosmology, events transition from an ancient cold state to a young hot state. The presence of this hot, dense state is a consequence of the preceding cold, void state. Nevertheless, this causal relationship does not conform to the conventional understanding of time, as both states lack normal meanings of size and time. The cold void state and the hot dense state exist on discrete timelines, which implies that, from the perspective of an observer within its own timeline, the cold void state would continue indefinitely. Here, physics and philosophy converge in cyclic cosmology, providing theoretical and detailed explanations for the origins of these cycles. However, regardless of whether Penrose's ideas gain traction in cosmological advancements, a deeper philosophical question persists regarding the true origin of reality itself. How did these cycles come into existence? This leads us to consider the justification for the existence of something rather than nothing, which remains one of the most profound inquiries in science and philosophy. The concept of vibrating strings of energy suggests the possibility of a cyclic universe emerging from certain definitions within string theory. This hypothesis posits that the universe could exist in higher dimensional spacetime, where the interactions of fundamental forces lead to phenomena such as expansion and contraction. While the cyclic universe theory remains largely speculative and faces significant challenges in terms of observational evidence and theoretical consistency, it strives to reconcile quantum mechanics with general relativity on a cosmological scale. Cyclic cosmology presents an intriguing idea of a universe without a definitive beginning or end, where each cycle builds upon the remnants of its predecessor. Despite its theoretical nature, various models and observational cosmology have provided valuable insights into the early universe and its evolution over immense timescales. The discovery of the cosmic microwave background (CMB) radiation in the 20th century offered strong evidence for the Big Bang theory, depicting the universe as it was just 380,000 years after its inception. Detailed measurements of the CMB by satellites like the Wilkinson Microwave Anisotropy Probe (WMAP) have allowed scientists to map temperature and density variations across the early universe with remarkable precision. Furthermore, observational cosmology has shed light on the large-scale structure of the universe, revealing a complex web of galaxies, clusters, and vast filaments stretching billions of light-years. By analyzing the distribution of galaxies and measuring their redshifts, astronomers have traced the history of the universe's expansion, gaining insights into its age, composition, and future. One of the most captivating discoveries in observational cosmology is the existence of dark energy, a mysterious form of energy that permeates the universe and is driving its accelerated expansion. First inferred from observations of supernovae in the late 1990s, dark energy constitutes approximately 68% of the universe's total energy density, making it the dominant component of the cosmic energy budget. Its existence poses significant challenges to our current understanding of fundamental physics, as its origin and nature remain poorly understood. Some theories suggest that dark energy may be related to vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's theory of general relativity to account for the observed acceleration of the universe. In their quest to understand dark energy and other fundamental mysteries, physicists are actively searching for new particles and interactions that could provide clues about its underlying nature. Facilities like the Large Hadron Collider (LHC) at CERN aim to explore the frontiers of particle physics by colliding protons at extreme energies, potentially uncovering new physics beyond the standard model. Advancements in astrophysical instrumentation have also revolutionized our understanding of the universe across various frequencies of the electromagnetic spectrum, from radio waves to gamma rays. Observatories such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have enhanced our knowledge of star formation, galaxy evolution, and the cosmic distribution of dark matter. Looking ahead, the next generation of observatories, including the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, promises to provide new insights into the early universe and its fundamental constituents. These cutting-edge instruments will enable researchers to study the first galaxies, investigate the epoch of reionization, and search for traces of primordial gravitational waves left over from the Big Bang. In conclusion, the pursuit of understanding the origins of the universe represents one of the greatest intellectual challenges of our time. From ancient myths and philosophical inquiries to modern scientific theories and observational breakthroughs, humanity's exploration of cosmic beginnings has yielded profound insights into the nature of reality itself. As we continue to push the boundaries of knowledge and inquiry, new theoretical frameworks, observational techniques, and experimental advancements will undoubtedly illuminate the fundamental mysteries of existence and our place in the universe. Key inquiries into our motivations will center on explanations within the realm of physical science. We will consider three possible outcomes in exploring the origins of these cycles. First, there might be no satisfactory explanation at all. Second, there could be a tedious series of cycles, where each cycle leads to an alternate universe, with the fundamental quantum state of each universe somehow influenced by aspects of its predecessor. Finally, there is the possibility of a single cycle in a repeating universe, where the start of the cycle is determined by some aspect of its own conclusion. These outcomes are intriguing because they eliminate the need for uncaused events and offer a more complex explanation within the framework of physical science. Roger Penrose proposes the idea of an infinite series of cycles, informed by his interpretation of quantum mechanics. In quantum mechanics, a system can exist in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose challenges this notion by suggesting that each cycle is influenced by random quantum events that lead to variations between cycles. This concept opens up exciting opportunities for testable physics, as it suggests the potential for identifying subtle traces or anomalies in the residual radiation from the Big Bang. The quest to understand the origins and nature of the universe has been a central mission for human curiosity and intellectual inquiry for centuries. From ancient philosophical theories to contemporary cosmological models, humanity has consistently sought to unravel the mysteries of existence itself. In the context of modern astronomy and cosmology, the investigation of cosmic beginnings has led to significant discoveries and captivating theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that has fascinated physicists and cosmologists alike is the nature of the universe prior to the Big Bang. While the theory explaining how the universe evolved from a hot, dense state to its current vast expansion provides a compelling account of this development, it leaves open the question of what preceded this extraordinary event, if anything. The idea of a pre-Big Bang era raises profound philosophical and logical implications, pushing the boundaries of our knowledge. Several theoretical models have been proposed to address this question, each offering unique insights into the early universe. One such model is the concept of the multiverse, which posits the existence of a vast collection of universes, each with its own specific physical properties and fundamental constants. In the multiverse framework, our universe is just one among many, each emerging from different initial conditions and governed by its own set of physical laws. The multiverse hypothesis naturally arises from certain interpretations of quantum mechanics and cosmological expansion theories. According to inflationary cosmology, the rapid expansion of spacetime in the early universe may have led to the creation of pocket universes within a larger multiversal context. Each pocket universe would possess its own unique properties shaped by random quantum fluctuations during the inflationary epoch. While the multiverse hypothesis remains speculative, testing it offers an intriguing answer to the persistent challenges in cosmology, particularly regarding the apparent fine-tuning of the fundamental constants of nature that allow for the existence of complex structures like stars and life itself. Another compelling idea that challenges conventional views of cosmic origins is that of eternal inflation, proposed within the framework of inflationary cosmology. Eternal inflation suggests that the universe undergoes an infinite series of inflationary phases, each giving rise to new regions of spacetime that may have distinct physical laws. In this scenario, our observable universe is merely one of countless regions within an ever-expanding cosmic foam. The notion of eternal inflation raises significant questions about the nature of time and causality within the multiverse. As inflationary bubbles continuously generate new universes, the idea of a singular origin or ultimate beginning becomes increasingly elusive. Instead, the universe appears as a dynamic and continually evolving entity embedded within a larger, boundless tapestry of inflationary expansion. Recent advances in theoretical physics have also sparked interest in alternative cosmological models that challenge the conventional narrative of cosmic beginnings. For example, some researchers have explored the possibility of a cyclic universe, where the Big Bang is not a unique event but rather one phase in an endless cycle of cosmic expansion and contraction. According to cyclic cosmology, the universe undergoes successive cycles of creation, evolution, and destruction, with each ending in a big crunch followed by another Big Bang. The cyclic universe hypothesis draws inspiration from ancient cosmological ideas and contemporary theoretical frameworks, such as string theory. Within the context of string theory, which posits that fundamental particles are not point-like but rather one-dimensional strings, the potential for cyclic processes becomes a fascinating avenue of exploration.